Okay. Why don't we get started? Sorry for being a little bit behind, and I'll apologize as well. I've got a cold, so hopefully I won't be kind of too distracting with coughing and things like that. But that's life. So here's the plan for today. We can start with some questions about exercise 2, and then we'll go into our topic for the day, which is about the diffusion equation and looking at some examples of diffusion as a geological process. And then we'll take a look at the exercise as well. The course webpage, course website's not yet updated, but I'll push these slides there probably after we finish the lecture. And if you're wanting to look, the slides are similar to what was up last year, so you could look at the 2018 version if you want for the course. But yeah, are there any questions about this exercise number 2? How are you guys doing with that? Is it a bit better than exercise 1 in terms of feeling a bit better about it, or worse? How many are totally done with exercise 2? So kind of, maybe not quite half. Okay, well, I've got some good news for you. Yeah. Okay.
Is it like the chi-square is more about the standard deviation and the chi-square like about the relation between x and y value?
Yeah, so the correlation coefficient is basically how well did the data fit a line. So in this case, that's the kind of simple model that's used there. And by calculating the correlation coefficient, the idea would be that for any line with a slope that is not 0, if the points fall exactly on the line, then you should get one of these correlation values of plus or minus 1, depending on the slope of the line. But essentially what it's measuring is how well the data fit a line as a model. So that's why when we looked in the lesson at these distributions of points that were kind of all over the place, you would get correlation coefficients of 0 because there was no line that would fit that data. The chi-squared value is more about, well, you don't necessarily have to have a model in mind in terms of like, you're not trying to fit your data on a line or fit some given curve. It's more about if you have an expected value and you have some standard deviation for that expected value, does the observed value fall within that standard deviation? Does the observed value fit the data? And so for that, you could take things like, we'll do something with it in the exercise this week. I mean, you could take things like elevations of the Earth's surface. If you have some model for what those elevations should be and you have some standard deviation, you could take something that's quite rough like the Earth's surface and calculate a chi-squared value for that. There's no expectation that it should fit some kind of linear profile. I mean, you could have a natural landscape, and if you had some model to try to reproduce that landscape that would give you an expected value, you could still calculate this chi-square misfit for that. So the difference in some respects is you're not trying to fit a line, but secondly, because you have a standard deviation, you're using that to sort of say, does my data fall within the uncertainty or the variations that's expected for this data set. For the correlation coefficient, you don't consider the uncertainty in any way. It's literally just how well do the data fall on the line, and that's that. So, yeah. Any other questions about exercise number 2? It's a good starting point. Yeah.
I have one. So when we talk about like changes temperature with time, can we use like slope as a coefficient like that shows how much temperature change or not?
I mean, in essence, that's one of the ideas with the fitting the data to this, relatively long-term trend, is that we have enough data that even with some scatter, because like each year we don't expect temperature to go up just following a line. We know that there's a lot more variability and things that affect climate that will shift the seasonal temperature values by a certain amount. And it's much more complicated than just saying, like, let's fit a line and expect the temperature just to increase following this line. At the same time, there is a trend there. And it's enough of a trend that if we consider the uncertainty and the kind of variability within each season, then we get some reasonably meaningful line that can be fit to that data that we could then potentially use to like forecast, or to go back in time. We could sort of, extrapolate back to what temperatures could have been for some period of time. I mean, obviously, the longer and longer we go back or longer we go forward in time, we're introducing error because we don't know. We only have a 65 or so years of data. But that was the kind of idea, was to say that, like, if we fit a slope or calculate the slope of the line that best fits this data, what does it show us about how temperature has been changing over this time period on average? And of course, there's a good amount of scatter around that linear fit. So you see, like, the correlation coefficients aren't great. I mean, we don't get something that's close to 1. It's
like awful coefficients.
Yeah. So I mean, that tells us that the data maybe doesn't fit a line very well, but still, when you calculate the chi-squared value, you get a pretty good value because you see the standard deviation in each season is pretty big. So in most cases, that line passes right through the uncertainties that you have there. So within the variation you expect in each season, the line fits pretty well.
It's like first step of analysis to check it.
Yeah, I mean, essentially it's just we wanted to take a familiar data set and just use that as a way to analyze it a bit further. And of course, it would be nice to have a really long time record, but the further we go back in time, we have to use other methods to getting temperature. We can't measure temperature directly, and then that means there's more uncertainty as well.
But is there any reason why guidance of fit and coefficient of correlation could have like a different shows different results? Like there is difference if it's not linear function, but what's more reason for this?
Well, I mean, that is exactly one of the things, is if it's not a linear function, like temperature is not a linear function just of time. So that correlation coefficient is really only going to tell us how well you fit a line function. Now, there might be some better function that fits the data a bit better, but still, without having some very sophisticated model, like our model in this case is a straight line. So without something more sophisticated, we can't fit the data and the variability we see with a line any better than we do. The correlation coefficient, and again, is only telling us how well the line fits our data. The chi-squared value is going to be telling us, if we consider the variation within the seasons, how well does that same model fit. Now, probably what we would see is if we used other functions, the chi-square value would also be pretty good, because you see that the standard deviations are pretty big. This is often also the case with geological data, that you have fairly big uncertainties on measurements that are made. So there are many different models that could fit the same data set. So then you have to start looking for reasons like, do we have some reason to believe that temperature would be increasing over time? Maybe we could look at concentration of greenhouse gases or something like that and say, okay, we have some expectation that if the greenhouse gas concentration goes up, then we should expect to see the temperature going up as well. And maybe we could try in some way to bring in some additional data to help rule out some models that could be used to try to fit the data. But they're kind of measuring two different things. So that's the thing that's a little bit tricky about it, is we don't necessarily expect to see the same thing from both. Yeah. Okay. So yeah, I started saying something about how I have some good news for you, and that is, if you haven't been watching on Slack, the deadline for exercise 2 has also been extended, like exercise 1 was. So exercise 2 is now due by the end of the day tomorrow, so 23:59. And what that means is that you should be able to get some assistance in the exercise work session tomorrow if you're still having issues with exercise 2. And in fact, for all the exercises going forward, we made the decision that we'll just go ahead and make the deadlines for all of them be the end of the day on Tuesday, the week after they're assigned, so that you have like 2 exercise sessions that you could work on the exercise if needed. Now, with that, we don't want to encourage you to not work on it the week that it's assigned and then put it to the second week, because that doesn't help you. So just think about that when you're tempted to do that type of thing. I was a student and often worked like that when I was doing assignments. If there wasn't a deadline that week, I didn't bother with it. So can't say that that's how I can't say this is how I would operate, but I would encourage you to work on the exercise, at least get started on it in the week in which it's assigned, so you have some idea of like where you might have problems the following week if you need to get some extra help. Okay, so yeah, you'll see that in the exercise 3 that the deadline is now bumped to end of the day on Tuesday, the week after. So, okay, if there's nothing else, then what we can do is move to our topic for the day. And you can see here we're going to talk about natural diffusion. The way we're going to do this for like this, I think this will be the way for the rest of the course, that we'll have a little bit of lecture material that'll be longer than the little bit that was on the course page previously. So could be 30 or 45 minutes of introduction lecture material to kind of give you the concept of what we're talking about in the equation we're facing today. Then a mathematical mathematical description, and then finally a couple applications for that equation. We're going to go now into like a sort of set of weeks where we meet a common geological equation and basically see how to use it. So the diffusion equation is where we're going to start, and this is an equation that can be used for really a huge number of different applications. We'll get into detail with one of them, but we'll start here. We're going to introduce the concept of diffusion as a process as a starting point. I'm sure that all of you are familiar with diffusion in varying to varying degrees. You've probably already experienced diffusion in different parts of your life on a daily basis, but we'll introduce the concept just to make it clear, then talk a little bit about the mathematical description, and especially in this first lesson, I'm going to talk a bit about how to convert some description of a process like diffusion in words into an equation, so you can see how the things basically translate from some kind of description in text to a mathematical equation. And then our application, the application for today is going to be on Hillslope diffusion. So typically nobody has had a course in geomorphology. I don't know if anyone has had a geomorph course before, but we're going to talk just a little bit about Hillslope transport process called diffusion that includes a number of different individual processes that basically serve to move sediment or soil down a hill slope. So let's start with the concept. The idea in general as a geological process is that diffusion comes up in a number of different places. And you've maybe heard about diffusion at the crystal scale when we talk about crystal defects and how they migrate through crystal as it's deformed. That can be modeled as a diffusion process. And in parts of the Earth, like in the Earth's mantle, that could be a process that leads to sort of large-scale solid state flow of the Earth's mantle. We can also talk about some of these hill slope processes like we'll see today. This is an example just of rain splash. So when raindrops hit the Earth's surface, if the surface of the Earth is on a slope, there's a tendency to splash more grains of soil or sediment, more pieces of material downslope than upslope. And if you can believe it, this rain splash process by itself can actually move sediment at a sort of measurable amount downslope from just from raindrops striking the Earth's surface. And perhaps you're also familiar with things like diffusion that can take place within a crystal. So if you have something like, this is an example of an inert gas, so helium trapped inside a crystal lattice, such as helium being produced by radioactive decay, helium isotopes will tend to diffuse through the crystal from the center out toward the edges of the crystal, and that diffusion process will have implications for things like geochronology. We'll talk about thermochronology later in the last 2 weeks of the course, but this diffusion process also comes up at the crystal scale, as well as things like heat conduction. So if we talk about conducting heat in the Earth, that's basically a diffusion process. So in terms of the general concept, it's a process that results in mass transport or mixing as a result of random motion of diffusing particles. So we'll take a look at an animation in just a second that shows a bit of this motion, but the mixing basically takes place by random movement of atoms. So here we have an example of 2 different atoms, doesn't matter what they are, atoms A and atom B, that are separated initially by some barrier here in red. And then underneath here we have the concentration of the atoms of material A. So you can see on the left side that the concentration is uniform and high, and as soon as you cross the barrier, that concentration goes to 0. If we set this thing in motion and basically take the barrier away and assume that these atoms are kind of free to change place with one another in a random fashion, what you see happen is that over time, some of the yellow atoms move to the left, some of the blue atoms move to the right, and the two start to mix. What you see initially is that the mixing takes place basically right at the boundary of the 2 materials, but then over time, they start to spread further and further apart from one another. And you can see this kind of red line moving off to the right. It's kind of marking the front of the blue atoms moving off into material B over time. If we were to follow any one of these individual atoms, they're basically just moving randomly in any of the 4 directions they could move. So if we assume you could move up, down, left, or right at any time, if you just allow things to randomly move, what will happen is that these 2 will mix, or these 2 materials will mix over time. And yeah, I guess this is probably a familiar process. Like I always mention, if I was like dumping some cologne on the front of the table here, that the people in the front of the classroom would smell it first, and then it would sort of make its way further back into the classroom over time. And the concentration would also perhaps decrease as this wave of cologne smell propagates, and that would leave it so that maybe it doesn't smell as strongly at the back of the classroom as it does here where the concentration's higher. But yeah, I guess the process itself is probably already something that's somewhat familiar. Now, the concentration gradient here is initially basically like a step function. It goes from concentration of A is constant and high to 0 across this red barrier. And over time, what you see is that that gradient, or the steepness of the barrier between the 2 materials, decreases. And so you see the slope of this concentration gradient going down over time. And that's basically another thing that happens with diffusion processes. There's a tendency that if there is a gradient, diffusion tends to reduce gradients. And you can think about this example from, if you have something hot and you put it in contact with something cold. Initially, the temperature difference is very high, but after some period of time, both things start to have temperatures that are more similar to one another. And eventually, if given an infinite amount of time, the 2 would have the same temperature. So that's our process. Now, yeah, so we talk about this random motion, and there's a tendency to transfer energy, to transfer mass from areas of high concentration to areas of low concentration. That's probably no big surprise. You've already got some familiarity with that idea. And the reduction of the concentration gradient idea is also meaning that basically if there's some kind of steep barrier, that will get less steep over time. It's concentrations of atoms A and B. The barrier between the 2, or the concentrations, will get to be more similar over time. It's temperature, whatever you want to pick for your diffusion model. So that's the concept. Now, if we want to be a little bit more quantitative, we can go for this more refined definition. And that is to say that diffusion occurs when a conservative property moves through space at a rate proportional to a gradient. Now, reading this I've read this definition a number of times, and I don't really get a great deal of information from it. It is probably a very good description of diffusion as a process, but it's not a very accessible description. And so this is what we're going to do now, is kind of break this down a little bit. So when we talk about a conservative property, it could be anything that is conserved within the system that we're looking at. So it could be energy that's conserved if we're looking at heat conduction, and we want to consider that process. We have a conservation of energy. If we're looking at these atoms of A and B, the two materials, we're conserving mass. But whatever it is, it's a conserved property within the system that we're considering here in order to model it as a diffusion process. The rate being proportional to the gradient is basically saying that the change or the movement of material will be in proportion to how steep the gradient is between the two concentrations. And so you see that when the concentration is high in the beginning of this animation that we looked at, that the material is moving perhaps more quickly, and as that gradient gets slower, the concentration is changing less over time. So, again, if you think about an example of two pieces of metal, one that's cold and one that's hot, if you put them in contact with one another, at first, right on the boundary between the two, the temperature change will be very rapid, but then over time, as the temperature difference gets lower and lower, the concentration, or the sort of concentration of energy, gets lower, and the change in temperature will decrease. So the rate of change of temperature will be slower over time. So this is our slightly more quantitative definition, and now we're going to take the next step and look at the mathematical definition. So this is where we can take this and try to convert this rather, I would say it's somewhat intimidating definition into some mathematical terms that might be a little bit easier to understand, and certainly something that we could more easily manipulate in Python. So if we want to start with the first, start first with the second part of this rate being proportional to a gradient, we could say something like that the transportation rate, or the rate of movement of these atoms, whatever, is proportional to a change in concentration over some distance. That's basically just another way of saying a gradient. So if we looked initially at our animation before, we had a concentration of atoms of A that was constant and high on one side and 0 on the other side. And the gradient we could calculate by just going across and saying from one position over here to the other position, how much does the concentration of this A change? So we're going to have something happening here, movement of material, that's in proportion to that change in concentration. We could put that in kind of more quantitative terms. Often concentration gradients are referred to as a flux. And, the flux is the transportation rate part of this. And so we could say that our transportation rate, or flux, is proportional to our concentration gradient. That's basically just rearranging what is said in the text above there. And then if we have it in those terms, it's relatively easy to then convert that to mathematical symbology, because flux is often represented with the letter Q. There are other terms that can be used there. And this sort of proportionality thing here is just meant to say that the two terms on either side of it are proportional to one another. So they're not exactly equal, but they're, with some kind of scaling constant out in front of them, they would be related to one another. And then the concentration gradient here is just the change in C, change in concentration, over some change in distance x. So this is just mathematically rearranging what we have here. I don't know why this guy always turns out to be so small. I need to maybe try to fix that on the slide. That little proportionality thing gets like micro size for some reason in this presentation software. But anyway, we can see here basically the steps to go from some definition in text into something more mathematical, which is to say Q is proportional to delta C over delta X. And this actually isn't so bad to look at. In fact, I don't know, maybe it's my bias, but I actually find that easier to understand than the text description of the diffusion process, because I could think about this in terms of like, I could think of delta C as like, okay, concentration of atoms A and B, delta X is some distance, and Q as a flux, sort of transportation term, I can think of what those things all mean. So we have our example here again of these atoms A and B. And if we want to go from our finite world of, some measured concentration over some measured distance or measured change in concentration, we can basically make things a little bit more flexible by going to these very small distances over which we consider a change in concentration, going from these capital delta for finite changes to lowercase deltas for infinitesimal changes. So that just means that we're going to consider very, very small distances over which we measure the change in concentration. We can keep basically the same color scheme and convert this equation to something that is much more like what the terms are that we see in the diffusion equation, and that is to say that this Q is equal to minus D times delta C over delta X. So now you can see that we've gone from being proportional to having an equality here, and our coefficient out here, D, is what's called the diffusion coefficient or diffusivity. And that could be a number of different things that could represent naturally, but it's basically a measure of how quickly the change in concentration will transport mass. So now we have eliminated that proportional to term, and we have a sort of equation for the second part of what we considered in our diffusion example. So, if we look at this now, we could put it in terms, as the projector takes a break, put it in terms of concentration of A, and in this case, what we would see is that our Q is equal to minus D times the change in concentration of A over some infinitesimal distance dx. And what we can see is that the concentration of atoms of A, for instance, is moving off to the right in the example that we have here, where we follow that red line. And if we stay actually in this case in the middle, what you're seeing is that the concentration of atoms of A is decreasing. Well, it's basically exactly 0 in the middle, but it's decreasing on the left side over time following this transport that we expect for a diffusion type process. So yeah, why is there a minus sign here? Any idea?
It shows how it decreased in the area it was. That's it.
Yeah, that's close. So if we consider 2 points here, maybe it's easiest to illustrate it this way. But what we would see is if we consider a point here, x1, with its initial concentration C1, we can see that it's basically got, a constant concentration of atoms of A. If we go over to the other side, we see the concentration of atoms of A is 0 at this point x2. So we could say, all right, well, let's see what happens between those 2 points. And so we would calculate what the difference is between the concentration. So if we took C2 minus C1, you're going to get a negative or a positive value for that. So it's concentrations of atoms of A. So C2 minus C1, positive, negative, negative. Yeah? So it's 0 minus some non-zero value that's positive will give us a negative number. x2 minus x1, if we take the difference between those two, positive or negative? Positive, yeah? Because x is increasing to the right, so x2 minus x1 will be positive. So we're going to have here a flux that says minus d times some negative number divided by a positive number, so that's negative for the delta c over delta x term. So then that means that if we take that negative term, multiply by negative d, that gives us something that's positive. So, right, two negative numbers multiplied together gives you something positive, which means we end up with a positive flux of atoms of A. And that's basically what we see, is that within this example we're considering, we see atoms of A moving moving off to the right and increasing the concentration at point x2 relative to the initial concentration at point x1. So that's the kind of example there. There's another piece of the equation we have to consider here, and that is this conservative property moving through space part. A little bit harder to formulate this in terms of words that we can understand. But we can think about this change in concentration with time as being our one part of moving our conservative properties, the change in concentration with time. That's the thing that's being conserved. It's equal to the change in transport rate with distance. So this is the moving through space part of this translation. And it is admittedly a little bit harder to directly translate this. But this conservative property basically is just, whatever the change is with time is going to be related to some kind of change in transport rate with distance. So another way we could say this is change in concentration with time could be the rate of change of the concentration. That's kind of relatively straightforward translation, is equal to a flux gradient. So we had this transportation rate thing before. If we have a transportation rate that's changing over a distance, that is another gradient. And so transportation rate is our flux, and the change in distance over some distance is the gradient part of that. This might take a little bit more time to sort of look at and fully understand, but once we have it in these terms, the rate of change of concentration is basically just delta C over delta T. So change in concentration, delta C, over some time, delta T. And that's equal to a flux gradient. In this case, it's minus delta Q over delta X. So Q was our flux before, X was our distance before, so that's our flux gradient in this case. And basically, this is just a way to ensure that we're conserving mass with this diffusion process. That is one of the things that that's expected to happen. Because we have a conservative property, we should have an equation that basically will conserve mass or conserve energy as part of the way that it's defined here. So how is this a conservation of mass or conservation of energy equation? I won't make you sweat through that one, but again, we can consider how the equation works. And that is to say that we have fluxes at different points. So we have some point x2 with a flux q2, some point x1 with a flux q1. And what would happen here if the flux of mass at q2 is larger than the flux at q1? So again, you don't have to put actual numbers in here, but what would happen if you put in some just value so that q2 is bigger than q1? What would you get out of here for your change in concentration? Would it be positive or negative? It won't be zero.
Negative.
What do you think? We have one vote for negative. Anybody else thinking negative? So let's go show of hands then. How many would say it's going to be negative? We've got like the original negative source. Sorry if that sounds bad, but original source of the negative answer and one reluctant supporter. How many think it's going to be positive by show of hands? So we got 3 and about 3/4 abstaining. So yeah, in this case, if Q1 is bigger than Q2, we should expect Q2 minus Q1 to be positive. X2 is going to be bigger than X1, following the same sort of thing that we had earlier. So positive number divided by a positive number means that will be positive as a term, and then the minus sign out in front of it means that the change in concentration would be negative. If there's more mass moving away at point 2 than there is at point 1, it says the concentration should be going down. Exactly the same thing would happen if we flipped that around and had more mass being transported away at point 1, it would say the concentration will be going up. And essentially all this is saying is that if we swap these things out, make them small deltas, that the concentration will change based on how much material is being transported at a given point. So I think if I was to pause this for example, we could see, if we consider the concentration at any one of these given points, that the concentration of atoms of A is higher here, and the flux is going to be in proportion to some gradient, so the transportation rate should be higher here than it would be at some point over here. And what that would say is that if our transportation rate at sort of Q2 is bigger, or sorry, Q1, if we consider the point here as our kind of X1 and X2 was somewhere over here, if this Q1 is bigger than Q2 over here, we should expect to have more material being transported from this region here over to the right. And basically that's what we're seeing, is that these atoms of A are moving off to the right with time. So again, we're introducing it here, and if you need to, it's not a problem to go back and spend a little bit of time looking through this if you want to try to fully understand how this diffusion equations is working, but that's that. So one thing to note here is that we won't go through the solving of the diffusion equation in any detail. In the past, I have done that, and it's not proven to be particularly interesting for the vast majority of the people in the class. But on the course page, you could find an example of how to solve the diffusion equation that puts these two different pieces that we just looked at together and solves for a given set of boundary conditions to allow you to calculate, in this case, it's a Hillslope elevation based on diffusion as a process for transporting sediment or soil at the Earth's surface. Yeah, are there any questions about this? This doesn't need to necessarily be crystal clear right now because things will become more clear, I think, in the exercises. But any questions for the moment about this diffusion equation stuff? Have you seen the diffusion equation previously? Or how many have seen diffusion equation before? Like a few? So, I mean, it can come up in a number of different capacities. If you've had a course on geophysics, you would have seen diffusion equation for heat conduction. But it can also be in, yeah, I think introductory physics courses sometimes would have diffusion equation in them, or even geochemistry and things like that might have diffusion equation come up. So there's a number of different places. Yeah. Yeah. So you may have seen this and not recognized it as the diffusion equation because sometimes it's introduced with some special name depending on the process. Like often for heat conduction, it might just be called Fourier's law, but it's basically a diffusion equation. Okay, so let's go on to our application for today. I'll spend a little bit of time here just to introduce the concept of how we could apply diffusion in one example. And this is going to be the example of looking at how material is transported on hill slopes. And so for this, I'm not assuming that you have had much of an introduction to geomorphology before. I'll go through a little bit of basic terminology so we can understand what hill slope diffusion is. But it's basically a way in which mass is transferred along the Earth's surface in a diffusion-like way. So that means that we have movement of material that's more rapid if the hill slopes are steeper and things like this. When we talk about erosional processes, we can talk basically about two different kind of classes, or you can subdivide things a little bit between things that are called short-range erosion processes. So these are things that are moving sediment over relatively small length scales. So typically it would be like hundreds of meters to maybe kilometers. And this is stuff that's basically happening on a hill slope. So like in a picture like the one here, I don't know why my mouse cursor is not showing up, but you can see, for example, when we talk about hill slope processes, we have ridges here and valleys here. We'd be talking about basically transported material along the hill slope between a ridge and a valley. And that's in contrast to long scale or long range transport processes, like things that happen when you transport sediment in a river, where it could go hundreds or thousands of kilometers. So much longer range transport for material, and a totally different transportation method, generally speaking, than what's happening on hill slopes. When we talk about hill slopes, of course, there's lots of different things that happen on them. You're probably most familiar with things like slides, so landslides, or examples of material where you have a coherent block of material sliding down along a hill slope, rock falls, and other kinds of things that are perhaps more exciting than what we're going to focus on today, which is this diffusion process. But then there's also things like flows, so debris flows and other types of mass movements where you don't have a coherent piece of material sliding down, but you've got a mixture of stuff that's basically rolling down the hill slope, and there's no obvious kind of like plane of weakness where the material has detached. And these kind of are the two exciting ones, and then down at the bottom of the list is something that we'll call heave. And this is basically movement of material that happens when the Earth's surface goes up basically perpendicular to the ground surface as a result of expansion of the material. So swelling of the material for various reasons results in movement of material downhill. We'll see what that means in just a second. Now, we don't need to spend a lot of time talking about all these different erosion processes, but just to give you a sense on this kind of ternary diagram between slides, flows, and heave, we're basically down in the bottom right corner of this thing, in the corner that is admittedly in the slow part of these processes. So perhaps not super exciting. In fact, creep is such a slow process, it's quite difficult to monitor. You can see the effects of creep over long time scales, but it's hard to monitor kind of over short time scales how the heave and related processes work. To give you a couple more definitions here, creep is essentially the thing that we're interested in understanding a bit with the diffusion equation. And this is basically a very slow process at which material is moved along the Earth's surface in response to gravity. And it's related to the heave process. Heave is basically when material swells up, and then once it's swelled up, gravity starts acting, and that will tend to move material down slope. And this is something that happens as like seasonal creep. So this would be something that could be observed here because there's a reasonably strong seasonality in terms of like a pretty cold winter, especially if you go further north into central Finland where the winter actually is properly cold. And then, the soil creep process that would be happening during the summertime even, as rainfall might saturate the soil and then lead to swelling of certain materials, and then some potential for creep to happen after that. What does it look like? Well, hopefully you can see. I know that the projector doesn't do a great job with this, so it might be easier to see the lecture slides once they're up on the course page. But this is an example of a shale that's nearly vertical in terms of its bedding. But you can see clearly that there is some transition zone within this shale bed where things have sort of tilted. And if you notice the tilting, it's actually getting a little bit more tilted as you go further toward the Earth's surface. This is basically material that has been affected by this creep process. So you can see a slope to the surface of the Earth there, and basically this is material that has been tilted and is moving gently downhill as a result of this heave and creep combination of processes. Here's another example, and this is perhaps something that you've seen. So I don't know that you necessarily have seen like power poles and things that have been tipped like this, but probably if you've been out in the forest anywhere, you'll see occasionally trees on hill slopes that have this kind of bent bottom to the tree. I guess maybe you've seen that before. And most likely if you haven't been someplace where there's like tons and tons of snow, that's the result of the soil slowly moving downhill, and it's basically taking the tree roots along with it and causing the tree to sort of tip. But of course, unlike the power line here, the tree will correct itself and start growing back straight up toward the sky. So you'll see, in places where this creep process is happening, the effects of it, that the tree trunk is basically bent close to the Earth's surface. That's because it's being transported down the hill slope as a result of this creep process. But then the tree itself will correct for that. I always mention that this is something that happens in places like we could see it in the forests around here, southern Finland. You could certainly see this if you went out looking for it. But in places where there's really deep snow, there is also a thing called snow pressure. So if you have really deep snow, like in mountainous areas, you can get bending of trees. It's also the result of the snow moving down slope and kind of pushing the tree along with it. So the tree could be anchored quite firmly to the ground, but then the snow can also cause this kind of bending of the tree trunk. They look a little bit different, but yeah, I guess you've probably seen examples of this before. So you might not have known it was a heave and creep kind of process, but that's what we're looking at. How does it work? Well, the basic idea here is that I mentioned that there's this expansion of material. So if you take unsaturated soil and add a little bit of water, you can get it to expand. Or if you've got kind of freezing of water that's in near the Earth's surface, of course, when water freezes, it's the volume will slightly increase. That also leads to an expansion. And when the expansion process happens, pretty much happens perpendicular to the Earth's surface. So when you swell material, you tend to basically have movement that's pretty much perpendicular to the Earth's surface, and that's represented here in the diagram by the little arrow labeled E. So that's the expansion part of things. Now, in theory, when the material contracts, it doesn't necessarily contract back to its original place, but this material that has sort of expanded out is being acted on by gravity and would tend to basically fall or want to move basically straight down parallel to the gravitational field. So again, since my mouse cursor is not showing up here, in this example, the line C here, this is supposed to be our hill slope, and we're assuming gravity is acting vertically down. The line C would be that if our material expanded following this vector E and then was acted on by gravity, it would tend to fall basically straight down on the diagram that we have here. And you can imagine if this process then says, let's swell again and fall down, swell again, fall down, that over and over, that basically, that is the process that leads material to move downhill slopes. Now, this is a kind of theoretical model, and in reality, the tendency is that the particle settling is not vertical, but would be something that's not going back along the same path where the expansion happened, but maybe slightly inclined. Regardless, the kind of process is one that you expand and then fall down in response to gravitation, and that leads to material moving downhill slopes. So that's the kind of the picture of what's happening here for the heave and creep process. Heave is the expansion, creep is then what happens when the material is moving down slope as a result of gravity. So considering this model and the fact that I could use a drink of water, what do you think is going to have an effect on things like the rates of creep? What do you think might matter when we consider this process? Just thinking of, what might affect expansion, what might affect the movement of material downslope. What kind of things can you think of that might matter here? That's a good one. The hill slope angle.
Material, like if it's consolidated or.
Yeah, whether something is kind of consolidated material or loose. Is there an amount of water, right? So basically, if we think about, how much does it expand? If we, there will be a limit at some point where if you add enough water, it no longer expands. But if you just add, one drop, maybe you don't get very much expansion. But if it gets a good amount of rainfall or something, you could get more expansion. Or if a bigger section freezes, Yeah, so those are some of the big ones, right? The slope angle is going to matter. If the slope is totally flat, who cares? I mean, the heave process will move its, do some things up and down. Maybe that would matter in some cases. It could possibly crack your foundation of your house or something like that. But if everything moves up by the same amount, maybe it doesn't matter. But yeah, that's the slope. That's going to be important in terms of this vector C, for example, in the diagram here. So there's a couple different things here. We pretty much got most of them that would matter. Slope angle, the amount of moisture in the soil or regolith, particle size, whether it's consolidated or loose, and the composition, right? If it's clay versus quartz sand, those two will swell different amounts when you add water. A lot of clay will expand quite a bit with water added to it. So, so those things will matter. The rate of transport is going to be strongly dependent on the hill slope angle. So generally speaking, up to the point that you get close to the stability of the hill slope, if it gets too steep, it could start eroding by other methods. But the steeper it is, the faster material will tend to move downhill. So in other words, our flux of mass is going to be proportional to the topographic gradient. This is starting to sound like a diffusion equation, as you might not be surprised to hear, since we're calling this hill slope diffusion. So sort of a slightly abrupt ending here is just to say that, okay, it looks like we have a diffusion process. We have some examples of how this can work for some geomorphic examples. And I think I'll skip over these questions. I put them here and I never actually ask them, so I should probably just stop doing it. But I will say, in the lecture slides online, you can find some other examples of hill slope diffusion. It's not just this heave and creep process, but there's in glacial landscapes, there's something called solifluction that happens when you've got melting of the sort of groundwater that's frozen in place, and near the soil surface. During the summers, you can have melting and movement of material along the Earth's surface and then refreezing at night. There's also rain splash, which I mentioned, and there's even things like tree throw, where when trees tip over, they tend to throw more material downslope than upslope, and even gopher holes, if you can believe it. When creatures bioturbate soil and get in there and dig around, they basically tend to kick more soil downslope than upslope if they're building their house on a sloped landscape, and that actually can make a difference, and that can be measured, and people have done this. So if you're interested in that, there are a few examples of these kind of other hill slope diffusion processes. The rain splash one is kind of nice because someone actually did this kind of laboratory experiment of like dropping water droplets onto sand with different slopes and like watching how the sand grains get flung with like a high resolution camera. So you can, if you're curious, see some examples of that type of process in the extra slides for the lecture for today. So, any questions about this heave and creep? That was the main thing we're talking about, just because that example has some nice ways of illustrating how material moves downslope and affects basically many landscapes where the surface is sloped a little bit. If there aren't questions about that, I'm going to just point out a couple things here. One is that if you are interested, when I put the new lecture slides up and just make the lesson 3 visible on the course page, there I mentioned you can find this example of solving the diffusion equation. So you can see our familiar pieces here, like our flux being proportional to a concentration gradient. That's converted to an equivalent thing for a natural landscape here. So this is an example of diffusion on a hill slope. So things are just converted a little bit to geological terms. So this D is replaced by a density times a sediment diffusivity, but you can go through this if you like. And then there's a mass conservation term as well that's similarly formulated in terms of the hill slopes. And then those two are combined and basically go through an example of how to solve for the elevation of a hill slope profile experiencing the diffusion process, how to apply the boundary conditions and things like that. Probably most of you won't spend much time on this page, and I can understand that. But I will point out at the very end of the page, there are some useful things that you can measure from this Hillslope diffusion model that you will need in the exercise for today. So you may, if nothing else, want to go to the very end of the page to find some of these things, like how to calculate what the maximum hillslope elevation would be for this model, because you're going to use that in the exercise for today. All right, so let's go here then to our exercise for today, and you'll see here that the exercise is about hillslope diffusion. No surprise there. It is due next Tuesday by the end of the day, and there are 2 problems for the exercise for today. Let's take a look here at what our 2 problems have. So this, by the way, this exercise 3 is available. The public version of it is up on the course page. So if you go to github.com/introqg-2019/exercise 3, you should be able to find this already, even though I haven't put the link yet live for the GitHub Classroom. So we are going to do a couple different things here. We're going to calculate some steady state diffusive hillslope profiles. What does that mean? Well, basically we're going to calculate a profile from one river across a hillslope to another river. So we'll get these sort of parabolic shaped elevation profiles for a landscape that is undergoing hillslope diffusion as its kind of sediment transport process on the hillslopes. It's steady state, so we're not going to worry about time. We could include time, but then we've got to introduce things like the error function, which makes our equations a little bit more complicated. So we won't worry about that for right now. So we'll do steady state hillslopes undergoing diffusion process. You're given an equation here. H is the height of the hillslope, or the elevation of the hillslope. So you can calculate H as a function of things like U. So this is the uplift rate and the kind of rate at which the landscape is being uplifted. I've got some issues here with unknown characters that need to be maybe fixed. And then kappa is our diffusivity for the sediment or the soil in this landscape. L is what's called the half width of the this hillslope profile. So basically this goes from the middle of it over to the nearby river. So it's not the full width of from one river to another, but it's just the half width. Maybe I will draw a picture of this in just a second to help illustrate things. And then X, of course, is going to be our spatial coordinate. Now, probably I can't do this in some way that the little camera here would capture it, but just to give you a picture of what we're looking at, we can take something that looks like this here. So if our distance along here is going to be increasing this way as X, elevation is going to be, in this case, the variable H, which gives us the height of the hillslope. And if we have some river over here and some river over here, basically the idea is that these are kind of some fixed elevation and our landscape is being uplifted in between them. And what you'll find is you get profiles that look something like this kind of parabolic shape, where in the middle at x equals 0 you have the highest elevation, and then over here the width of this whole thing would be 2 times L. So remember that L is the half width. I'll say it several times because every year this is a bit of a point of confusion of what L means. So it's only half of this hillslope profile. We're looking basically at a cross section, so like we would have rivers that would be flowing out of the screen or into the screen, out of the board or into the board in this picture. So our rivers would be flowing out, whatever, down this way and down like this. So we're kind of looking just a slice through some hillslope, like a cross section. Does the picture make sense in terms of what we're looking at? Yeah, okay. Because if that doesn't make sense, you're going to have a hard time with the other parts. So that's the kind of general idea of what we're looking at with this equation. And I'll kill that just so that we can see a bit better. So of course, in keeping with what we've done for the last couple exercises, step 1 is going to be make a function for calculating this Hillslope profile. And it might seem like a bit tedious or whatever to keep making these functions, but it's good practice because this is a good way to do your coding, that you should be writing functions as a way to convert these equations and make them easy to use. So you'll first make your Hillslope diffusion function. You'll see it takes a number of different parameters. So L is our half width, X is our array of distances, U is the uplift, and then kappa is that diffusivity term. So those things go in, and out should come the elevation H from that. There's a number of tests that you can see here, some fake data with L values and X values and things like that. And you can see then what whether your equation that you've converted to a function is working properly by running this set of tests. And there's actually 2 different sets of fake data just to make sure that if you get it to work for one case with a certain L value, that it doesn't not work for the second case. So you can test your equation once you've made it. Then you'll go through step 2 to calculate a Hillslope geometry. So you're specified here. We give you basically the distance between the 2 rivers, uplift rate, and diffusivity, and your job is to then calculate a Hillslope profile with those values. That should be relatively straightforward. If you've defined the equation above, you basically just use that function. And again, there's a couple tests here that show whether or not you've done that correctly. And then after that, you make a plot of a profile that should look somewhat like what's on the board there. To do this, we're going to basically take what comes out of your Hillslope diffusion function. Should be some variable, maybe H would be a good thing to call it. Put it into a pandas data frame and then plot. So it's kind of like what we had done in some of the earlier exercises where we had some value that was calculated, put it into a column in a pandas data frame, and then you can plot the results using the normal pandas plotting. So in this case, we're going to call our column default, and then you'll plot that with a black dashed line and add a few things on here. So I mentioned that you might want to take a look at that how to solve the diffusion equation thing. That's because we want you to put in text on your plot what the maximum slope is, what the maximum slope angle in degrees is, what the maximum relief, kind of highest elevation or biggest distance between the rivers and the and the top of the Hillslope profile, and then what the characteristic time scale is. You may need to sort of look at that one a little bit, but this is basically just a measure of how quickly the landscape would respond to a change in one of the parameters. So if we change the diffusivity, how long does it take to respond and come back to a new steady state landscape? And you'll see that this tau term will depend on things like how big the landscape is and how quickly it can respond based on the diffusivity. So you'll put those things as text on your plot, and then you'll add a figure caption, and that should be that. Then after that, we can take basically the same type of thing that was done in the first 2 parts and just redo it for some different values. So like if we double the uplift rate, how does the landscape change? If we double the diffusivity, how does the landscape change? So you'll add these as extra columns into your pandas data frame. And the idea is that when you do these calculations, of course, you'll also make a plot. And what's asked is that you plot first the case you calculated in part 3, so this default case, and then you plot the version for twice as high uplift rate or twice as high diffusivity, so that you can see the 2 on the same plot and see how increasing the uplift rate, decreasing the diffusivity, whatever it is, how that affects the resulting Hillslope profile. So there is one variable we don't play with here, and that is the length. You can play with that as well, but it makes it a little bit tricky with how the data frames are set up. So we won't do that until part 2. But basically, yeah, you're going to make 3 plots here, And there's a little kind of subsection heading for each plot and a place for you to put those in the notebook. So after that, then there's a couple questions, just general things about this, these Hillslope profiles, and then it's on to problem number 2. For this, we're going to take a trip to California. Unfortunately, only mentally, but we'll go to the western side of the Sierra Nevada mountains in California and look at a Hillslope profile here that was extracted between 2 rivers that are draining into the, I don't know if it's the Yuba or which, yeah, I think it is the Yuba River. 2 tributaries to the Yuba River. So we've got our profile A to A prime here that's from a natural landscape. What that means is first we're going to read that in. So we've got a data file to read, standard operating procedure here. Here's what our data file looks like. We've got some distance and some elevation. You're just going to read that in using pandas as we've done before. So that should hopefully be pretty straightforward. Once you read that in, this is our topographic profile data. So there's the one river over on the left, the other on the right, and you can see the elevated landscape in between. Looks a bit like a parabola. So that should perhaps give you some information that we're going to be looking at this as a diffusive hill slope. So for this, in order to deal with it, we're going to do a couple calculations, find out what the value of L would be for this natural landscape. So you have this hill slope profile here. You say, what's the half width? We can find that, and you're even told how to do that. And as well as the points along here at which you're going to calculate the elevation, those are also, you're kind of given clear instructions about how to get those values. And there's a reason for that will become apparent in just a moment. So once we've read in this data file and calculated a few values, we'll plot again one of these hill slope profiles, this kind of simple model of the parabolic hill slope profile for our natural landscape, so going to much bigger scale than what you're dealing with in problem 1. So again, we'll fill in some values here for our natural case and make a plot as well. I think that should be in here as well. I didn't list it explicitly in the comments, but there is something here that says you should do a plot. And then after that, it's time to make one more function. This should look somewhat familiar. This is a version or similar to our chi-squared function that we dealt with earlier. The thing is, we don't have standard deviation for the elevations here, so we're going to deal with a different version of the chi-squared value where all we're going to do is divide by the expected value on the bottom rather than standard deviation. And you'll note also that this is not squared on the bottom as it was when we dealt with standard deviation. So we'll have a difference between the observed profile and the model, which is E, and then divide by the value for E. Basically, at each point along our profile, we know what the observed elevation is, and we can calculate what the elevation should be for our simple hill slope diffusion model. Take the difference between the two, square it, and then divide by what the expected value is. And if you sum all those together, it gives you some way to look at the goodness of fit. Basically, the way this works, as you'll see, is if we get a landscape that doesn't look very much like our observed one, we'll get a big chi-squared value. If we get one that looks reasonably like our landscape, we'll get a still pretty big chi-squared value. But don't worry about that. I mean, this is not supposed to be a value close to 1 in this case because we're using a different equation. So I'll tell you the value should be somewhere, if you're getting a pretty good fit, it should be somewhere around 1500. You'll be able to test and see whether your equation works properly here. So you should know if your equation is giving you the right values based on the tests here. It's working properly, but I'll tell you that the chi-squared values you're going to calculate when you compare the natural landscape to our model are still going to be pretty big. Much bigger than we dealt with in the lesson previously. And that has to do with the fact that we're doing a different kind of calculation with a different equation here. So the last step here, and I maybe need to fix one thing. I don't know if the point total's right on this part 5, but the last step is basically to try to fit our model to our observed landscape. We have all the quantitative tools we need to do that. We've loaded in our data file. We have a model for how to predict what a hill slope profile should look like. And we have this chi-squared equation to allow us to compare our model to our natural landscape. So the idea here is to try to get a good fit based on changing the uplift rate. So if you look at, we won't vary anything else besides the uplift rate, but if you vary that, you'll see that if it's, a high uplift rate, you'll get a landscape that doesn't look like the observed profile. If it's really, really low, you won't look like the observed profile. So you're going to use your goodness of fit to try and find the uplift rate that gives a reasonably good match to the natural landscape. After that, you'll add a couple things to your plot, some text that says what the best fit uplift rate is and what your goodness of fit value is for that uplift rate. And you'll make a plot that shows the hill slope profile that is read in, the one that's up here, and then your model along with it, so we can see how well the two visually match one another. That's that. So you won't go from part 5 to part 4 here. I'll fix that so that going to part 6. But that's basically what we're up to for this week. How about questions? Are there any? So we're dealing with a new equation and sort of a new kind of concept. But I think in some ways, the plotting part, making functions part, some of this stuff should hopefully start to get a little bit more familiar and more comfortable, so you know how to get started on these things. And if there aren't any questions, I suppose what I'll do is I can stop talking and you can maybe start looking at this. Give me a couple minutes just to update a couple little typos that I noticed in here, and then I will make the GitHub Classroom link live so you can make your copy and get started on the exercise if you would like. So yeah, we'll stop here and I'll let you know when the exercise is ready.